Picture yourself in a field looking at your surroundings. What color do you see? Whites, greens, yellows, reds? You can almost see the rainbow. But wait, there's blue and purple. Why aren't they so common? Well, there's actually science behind the reason, believe it or not. First off, most color pigments cannot be made in our bodies. But what about those with blue eyes? That part is based off of the structure of our eyes, not the pigment itself. So why are there some animals that are blue, like fish and reptiles? The color blue in animals are due to the microscopic structure of their scales and interference of light. Interference of light is when two rays of light collide. One ray is entered and passes through, versus the other one enters and hits the other ray, and it cancels each other out. When both rays pass through and bend at the correct angle, this causes the color blue. So why is there such a lack of blue in nature? Plants use a red pigment called anthocyanin for their blue color. They use the red pigment and mix it with other color pigments to create the color blue. Now what about purple? We know by looking through a place that sells flowers that it's definitely more common than blue. But why? Remember those red pigments plants use? They use those same pigments to create purple. They're able to protect themselves from the sun because purple is on the opposite side of the color wheel from yellow, so they can cancel each other out. Birds and insects, on the other hand, are able to display the color purple by what's called structural coloration. This is where tiny structures in scales or feathers are used to reflect light. Why do we see different shades of purple instead of one? This has to do with the color spectrum of the fact that purple is in between blue and red. In fact, purple is not one of the colors of the rainbow and doesn't have its own wavelength according to Isaac Newton. Violet, on the other hand, does have its own wavelength and is known as a spectral color. Monochromatic violet light cannot be produced by the red, green, blue color system, the method used to create colors on a television screen or computer display. Here's an example of the red, blue, green color scheme shown by the slow-mo guys.
Set to my minimum focus. As I slowly move towards the screen, it becomes sharper, and you will then, at the last minute, see a very odd looking pattern. And what you're seeing there is an effect caused by the camera, this camera, trying to resolve individual pixels on the surface of this screen. Not close enough. In order to get closer, I'm going to need a macro lens. As I approach the white and everything starts to become in focus, you can see that white isn't so white anymore. It looks like I have to go closer even than that. Well, this close, it's a different story altogether. I'm gonna get a tripod. We're so close up right now that I can actually disturb this image by blowing on the lens. We're now looking at the sub-pixel level. A pixel is made up of 3 sub-pixels, red, green, and blue, RGB, you may have heard that before, and this creates the illusion of different colors. By dimming and brightening different sub-pixels to different intensities, this screen can create the illusion of literally millions of different colors.
In fact, the only colors used in the color system are, spoiler alert, red, blue, and green. So how can we see colors other than these 3? The L cone in our eyes are sensitive to 2 different regions in the visible spectrum, letting us see the yellow-green region. Another part in our eye is the S cone. This allows us to see the violet part of the color spectrum. This means our eyes create an illusion of seeing more than 3 colors. Hematite and manganese are the oldest pigments used for the color purple. They were used by Neolithic artists in the form of sticks, like charcoal, or grounded into a powder and mixed with fat to use as paint. Hematite is a reddish iron oxide and when ground coarsely makes a purple pigment. Manganese was used to color glass purple. The first synthetic purple, called Han, was invented in China around 700 BC and was mostly used in pottery and wall paintings. Chemically, Han was very unstable and sometimes resulted in a blue tint. During the Middle Ages, the pigment purple was created by using blue azurite or lapis lazuli with red ochre, cinnabar, or minimum, also known as red lead, that has a brownish yellow tint. The first modern synthetic color in the purple family was cobalt violet, created in 1859. This was also the first stable pigment that had a low tinting power, which made it quite expensive. The reason we associate purple with wealth is because of this. In fact, Queen Elizabeth I forbade anyone except close family members to wear the color. The Persian king Cyrus made a purple tunic as their royal uniform. Some Roman emperors restricted their citizens to only wearing white and earth tone colors like brown or green. It wasn't until 1856 was when William Henry Perkin created a synthetic purple and was less expensive, making it a color the lower class could wear. He first called it Tyrian purple, but renamed it mauve to sound more fashionable. Perkin invented the color using the mucus of sea snails, also called murex. One myth is that Hercules actually discovered the color after picking up a murex snail from a beach and noticed his dog had purple drool. It's surprising that the snails didn't go extinct considering the high demand for color. Now we understand purple is made both naturally and synthetically. There's another twist that involves chlorophyll. Chlorophyll molecules soak up blue and red light, but not green. We just see green because that's what our eyes process. Anthocyanin absorbs green and yellow light, causing the leaves to give off a deep red or purple hue. These leaves still contain chlorophyll, but the green is masked by the strong anthocyanin pigmentation. There are even some plants in rainforests with purple undersides. Scientists believe this protects the leaves from fungal infections. Since we know blue can't be produced by plants, why not animals? Mammals produce melanin, which is responsible for the color of hair and fur ranging from black to sandy red. Although they can produce melanin, they cannot produce other pigments. The range of pigments depend on what they eat. So we've established the fact that it's our eyes that manipulate the colors around us. Red, green, and blue are the additive primary colors of the spectrum. Combining a balanced amount of these colors creates a pure white. By adding different amounts of these colors creates other colors in the spectrum. The retina is covered by millions of light-sensitive cells, some shaped like rods, some shaped like cones. These receptors are responsible for processing light into nerve impulses and passes them along to the cortex of the brain through the optic nerve. Rods transmit black and white information to the brain versus cones transmit high levels of intense light, creating the sensation of color and visual sharpness. There are 3 different types of cones in our eyes: long, medium, and short wavelengths of light. The longer the wavelength, the warmer the colors. This is why humans can perceive warmer colors better than cooler colors. There are roughly 8% of men and 1% of women who have a form of color impairment. The most common impairment are problems distinguishing the difference between red and green. Other impairments affect other pair of colors. Full color blindness is actually very rare. Most mammals see the full spectrum, but some insects, especially bees, can see ultraviolet colors that's invisible to the human eye. Coming back to purple, did you know that it's the most refracted color of light passing through a prism? It's also the hardest color for the eye to discriminate.